Good morning, or good afternoon, whichever the case may be. Welcome to this webinar on providing evidence of compliance with incidental take permits. My name is Manuela Huso, and I'm a research statistician with the U.S. Geological Survey in Corvallis. My colleague and co-presenter, Dan Dalthorpe, is also a statistician with the USGS here in Corvallis. Before we get started, I'd like to thank Rick Amadon and TJ Miller from Fish and Wildlife for organizing this webinar, and the Fish and Wildlife Services Regions 1 and 3 for their strong support of this work that's actually applicable to any region considering issuing an ITP for any species, ranging from Indiana bats to golden eagles. And, of course, I would like to thank you for your interest in what we have familiarly come to know as evidence of absence. That's what we've named the software that we've produced, but what might be more aptly called evidence of compliance. As many of you know, requests to the U.S. Fish and Wildlife Service for incidental take permits from wind developers have been rapidly increasing in recent years, to the point that it's starting to feel overwhelming for some wildlife managers. Before issuing the permit, managers must assure that any incidental take is already minimized and that the taking will not reduce likelihood of survival and recovery of the species. So the first question is, well, how many is that? This is determined typically through collision risk models or through evidence from similar sites and through knowledge, sometimes very little, of what populations can sustain. In this example from a facility in the Midwest, the number that they arrived at was 3 Indiana bats and 2 northern long-eared bats. That might arrive somewhere out here over the course of a year. Often the permit states that if the permitted number is exceeded, the company will have to compensate through some form of additional mitigation or minimization, which can sometimes be quite expensive. So the question we're interested in is, how will we know when the limit has been exceeded? Or, how can we be reasonably sure that the company is in compliance with its ITP, both in a given year or over the course of the life of the permit? So here's what we're facing. Out there, somewhere, there might be no Indiana bats actually, but on the other hand, there might be some. Same for northern long-eared. When the ITP was issued, we used the best available science to determine that we think there will be 3 Indiana bats and 2 northern long-eared bats taken in a typical year. Does this mean there will be exactly that number every year? Well, quite unlikely. So in any given year, there might be 5, there might be 10, but there also might be 50 out there. If we didn't have enough information to accurately set the ITP level, we could be quite wrong. So how can we know, given what we find, that it's closer to 1 or 2 than 50, if we only find only 1 or 2 or maybe even none in our searches? Well, really, it all depends on the probability of detecting a carcass, or equivalently, the probability of missing a carcass. Why do we miss some carcasses? Well, all you have to do is look at the sort of landscapes that we're dealing with, and you intuitively know that it's quite likely that we will miss some of the carcasses on our searches. But we can quantify our chance of missing a carcass by looking at our protocol and the reasons for missing them. In a typical search protocol, we start by designating an area around a turbine to be searched. This area can vary from facility to facility, from study to study. But in addition to having variable search areas designated, there may be parts within it that are just too dangerous or brushy to actually search. Within the searchable area, we do our best to systematically comb the area, searching for fallen birds and bats. But what we find is certainly not necessarily all that was killed. First, because we often only search a subset of the turbines. Some animals land outside our designated search areas, while others might land inside but in unsearchable areas. Some carcasses are removed by scavengers before we can even find them, and some are present but missed because they fall in a hole, in a deep clump of vegetation, or shadows hide them. Just chance. Searchers don't find them. So there's many reasons combined why we don't find everything that's out there. But in order to estimate fatality accurately, we first need to estimate what the probability of detecting a carcass is, so that we can understand what fraction we have actually observed. So let's briefly go through all these components. First, we'll start with the proportion of carcasses in our searched area, which depends on the relative density of carcasses and where they land. This composite image of bat carcass locations across several turbines shows a higher density in the center than towards the edges. If rather than using this particular configuration for the plot search, or the search plot, we were to reduce it by 25%, well, we wouldn't necessarily be losing 25% of the animals out there. If we simply shrink the plot by removing 25% out of the perimeter, we'd only lose maybe 1%, maybe 5%, certainly not 25%. On the other hand, if for some reason the center 25% of the plot is unsearchable, we'd lose only about 85% of the bats at this site. The question to answer then is not what fraction of the plot is searchable, but what fraction of the carcasses can we expect to be in the searched area? One approach is to model the density as a function of distance, taking into account search effort, or essentially detection probability. This model that shows that the relative density is highest at about 20 meters and tapers off to 0 at around 80 meters can be translated into a three-dimensional surface that integrates to 1 and associates a relative density with every point beneath the turbine. The light color in this graphic, close to the center, indicates that we have a higher probability that an animal will be in the square meter near the turbine than farther from the turbine where it's dark. So what if we were able to search a plot with this kind of configuration, essentially only the roads and paths and the area very close by? If we don't consider the different densities at different distances, we would say that since we searched only 25% of the plot, we would find 25% of the carcasses. However, if we take that three-dimensional surface that we had before and superimpose that on this plot, we would say, although we searched 25% of the plot, within that searched area, we would expect to have about 60% of the carcasses. We'll see later how we can use this idea to our advantage when considering coverage in a study design. Our next factor, carcass persistence, is typically measured by placing trial carcasses in the landscape and recording how long it takes before they are removed by scavengers or otherwise no longer identifiable as a carcass by a searcher. When we do this, typically a carcass may be removed, but feather spots or feathers may remain behind. Those would be identified as a carcass, or at least as a former carcass, by a searcher, and so those are included as still being identifiable. Our next factor, searcher efficiency, is also typically measured by placing trial carcasses in the landscape and recording whether a carcass is observed by a searcher. Often searcher efficiency depends on vegetation as well as carcass size and perhaps even coloration. Just for fun, I'm showing you what I hope is a pretty rare event, but was captured by Michael Schirmacher of Bat Conservation International to show a lonely bat on the top of the nacelle of one of these turbines. Of course, we're not typically searching that area. To put this in algebraic terms, we start with m, the actual numbers killed at a site. But we know it doesn't necessarily equal x, the observed number of carcasses. Only the fraction that we call a, that arrives within the searched area, is even potentially detectable. Of that, then, only a fraction r of those remain unscavenged until the next search. And finally, a fraction that we call p of those that arrive in the searched area and remain unscavenged will actually be observed by a searcher combing the area for carcasses. So with this equation, we can see that it's the product of these three proportions that forms the overall probability G, that an animal struck by the turbine will be detected during a search. Actually, it's not quite that simple. The equation for G really looks something like this: the double sum of the product of an integral. But for our purposes and for just thinking about it as the product of these proportions gets us a long way. So we can take this equation and simply rearrange it so that we estimate m, the total number killed, by dividing the number that we observe by the probability of detection. We should note that because all the factors in the denominator are less than 1, that the estimated fatality can never be less than what we observe. To put some real numbers on this, let's say we had a site at which 28 of the 40 turbines that were out there were searched. And our search radius, or our search configuration, was such that we estimated 51% of the carcasses that could land out there to be within our searchable area. Scavengers removed about a quarter of the carcasses before we had a chance to search, and the vegetation, etc., and chance prevented searchers from finding about 40% of them. Each of these proportions by itself doesn't seem particularly small, but when you put them together, it results in an overall probability of about 0.16. That's the same as finding about 1 in every 6 carcasses that arrive, or from another perspective, missing 5 out of every 6 that arrive. In addition, we really don't know G, and we have to estimate it, so there's uncertainty in that 0.16 number. Perhaps we have a 95% confidence interval around G that says it's likely between 0.07 and 0.25. If we find a substantial number of carcasses, we can use this estimator to arrive at a 95% confidence interval for M that extends between 124 and 443, for example. And while this is a fairly large interval, for many purposes this is often quite useful. What happens, though, when we don't find any animals? To bring this idea into more familiar context, let's consider an analogy to a parlor game. We're at a party, and someone says, "Hey, let's play Stump the Statistician. We need a volunteer." So I'm a good volunteer, and I leave the room. The rest agree to roll the die 5 times. When I come back, they report, "We rolled no 6s. How many times did we roll the die?" So I'm a good statistician, and I know how to calculate the best answer. I divide the number of 6s observed, that's 0, by the probability of rolling a 6 on any given roll, that's 1 in 6, or 0.167, and the answer is 0. The party breaks into laughter. They loved stumping the statistician. The answer was 5. So what happened? In this analogy, a roll of a die represents a carcass killed. So 5 rolls, 5 carcasses. The probability of a 6 represents the probability that the carcass will be detected in our search process. It's as if for every carcass we roll a die. If it comes up 6, which it will on average about 1 in 6 rolls, we find the carcass. If it doesn't, on average 5 out of 6 rolls, we don't find the carcass. In this case, it just happened that none of the 5 carcasses were found. Our job as statisticians is to play that game, Stump the Statistician. Guess how many carcasses there are based on how many carcasses we found and our estimate of the probability of finding a carcass. Now let's look at this graphically. On the x-axis is the number of possible rolls. It could be that they didn't roll at all. Or they could have rolled once or twice or maybe 20 or 25 times. On the y-axis is the probability of observing what we did, that is, observing 0 6s, given the number of rolls on the x-axis. Of course, if you don't roll, then the probability of observing no 6s is 100%. This is in fact the most likely case, and it is the maximum likelihood estimate. But it's just barely more likely than the next case, when we roll once. Even if you roll 9 times, there's still a 20% chance that you'll observe no 6s. This means that if your overall probability of detecting a carcass is 1 in 6, then even if there are 9 dead animals out there, you have a 20% chance of observing none of them. It's not until you roll 17 times that your probability of observing no 6s drops to 5%. So really, it wouldn't be too surprising for us to have 10 or 15 animals out there and observe none of them. So the main point I'm trying to make here is that even if we know precisely the probability of detection, which we don't, although we do with the roll of a die, but we don't in practice, the best we can do is bracket the range of possible fatalities. In this case, we can be 95% certain that there were fewer than 17 animals out there, having observed none, and having a 1 in 6 chance of detection. But now let's change the game. Instead of rolling a die, we flip a coin and count the number of heads observed. Again, the party reports 0 heads, and again, I estimate no flips. In fact, no matter what the probability of the event, when 0 observations are made, my Horvitz-Thompson estimator, the maximum likelihood estimate, will always give the best guess as 0. But more troubling, it will not give me any bracket on my estimate. The variance around this is also 0. I show you now the same graph as before, but modified to reflect the probability of observing a head as being 0.5. In this case, given that we observed 0, we can assert with 95% credibility that we flipped the coin 4 or fewer times. Or, if this were a real-life search process, having observed 0 animals, we could assert with 95% credibility that there were 4 or fewer animals killed. But we can't claim, that is, we don't have evidence, that there were indeed absolutely none, even though we didn't find any. So my second point is that by increasing the probability of detection, we can narrow the bracket around our estimate of fatality. As the probability of detection approaches 1, the more evidence we have that the actual fatality was indeed 0, or very close, when we observe none. Our current site monitoring protocol and statistical tools that we have for estimating actual fatality from observed carcasses are fairly robust when the number of observed carcasses is relatively high. But a non-zero estimate of the dead population using a Horvitz-Thompson-based estimator can only be achieved if at least 1 carcass is found, and even then it is likely to be biased, particularly when we don't know the detection probability. This type of estimator is not designed to address compliance. When we expect to find a small number of carcasses, or maybe even 0 carcasses, we need a new protocol and estimators that can give us precise estimates and allow 0 or few observed carcasses to provide evidence that a company is likely in compliance with its ITP. The approach we've developed is based on Bayes' theorem, and it's appropriate when we expect low numbers or even no observed carcasses, and when we need precise estimates that the set limit has not been exceeded. Our focus changes from asking, what is the estimated fatality given our observed count and our probability of detection, to what is the minimum level of take we can reasonably rule out given our observed count, which might be 0, and our probability of detection. With that, I would like to now introduce Dan Dalthorpe, who will talk about the approach that we've developed based on Bayes' formula, talk about the evidence of absence software that he's written, and give examples of how the software can be used to design protocols and estimate likelihood of compliance at sites with ITPs.
I'm going to start out by estimating the total fatality of the Indiana bat in a single season to show how the evidence of absence software takes into account all of the factors that Manuela discussed in her excellent introduction. We'll start off with the sampling coverage, which is the fraction of carcasses that land in the searched area rather than the fraction of the total area that has been searched. What goes into the sampling coverage is the fraction of turbines searched, the search radius, and the unsearched areas within the search radius. The next very important factor is after the carcasses arrive in the searched area, they have to persist until they're actually discovered on the ground. So we model the scavenging process using a persistence distribution. The exponential model is the most common and it's the most familiar, but we've also included the possibilities for some other more flexible models that, in practice, end up fitting the Carcass persistence distribution a lot better. So here is a plot of the fraction of carcasses that remain in a search trial versus the number of days that the trial has been going on. And the best fit exponential function is shown, and it doesn't really fit the line very well. But a Weibull gives a lot better fit, and that's fairly typical. Also typical is if the log logistic or the log normal fit better as well. The next factor that goes into the estimation is the searcher efficiency, or the probability of finding a carcass given that it's out there at the time of search. And in this particular example, we're going to find 50% of the carcasses given that they're there at the time of the search. You can also see with the searcher efficiency a confidence interval. And that's because this is based on field trials where even if we know that we found 10 out of 20 carcasses, there's still some uncertainty about what the actual searcher efficiency is. It's going to be could be 50%, it could be 60%, it'll be around 50%. The 0.4 to 0.6 range, 0.5 searcher efficiency is typical of what you'd see if you have 100 carcasses in your search trial. So if we take these three basic parameters, the search coverage, searcher efficiency, and the probability that a carcass persists until the first search afterward, we can combine those into a rough estimate of the overall detection probability, as Manuela discussed earlier. But multiplying those three factors is only a rough estimate. And there are two big issues. One is it assumes that a carcass that's missed in one search cannot be found in a later search. We know that's not true. A lot of times, if a carcass is missed in one search, if a search comes along within the next few days, there's a reasonable chance you can find it in the next search. But if the carcasses are missed in one search, they're probably less likely to be found on the next search because carcasses tend to deteriorate with age. They get covered with dust, they get covered with leaves, they blow into a hole, they get dragged around and hidden by scavengers partially. Also, the easy to find carcasses are removed first, and so in later searches, the more difficult carcasses remain, and so naturally the searcher efficiency is going to decrease with each successive search. Evidence of absence includes a parameter for that, and it's a K parameter we call it, and it's the factor by which searcher efficiency changes with each search. And K can be estimated along with P in the search trials. You can enter the sampling dates, what dates you have sampled. Enter an arrival function. The arrival function tells when the carcasses arrive in the system, at what point in the season. In most normal circumstances, the arrival function is not important. Where it might be important is if all the carcasses arrive at the very, very end of the monitoring season, or if they all arrive at the very, very beginning of the monitoring season. All other patterns really will not have much of an impact in most cases. So in that case, we just pick the uniform, which is the simplest. And we can take some shortcuts in calculation if it's uniform. The final box is for inputs is the prior distribution. Is a important part of the estimation because we base it on Bayes' theorem, which requires a prior distribution. There are two big advantages for using Bayes' theorem over classical statistics, and the first is that it gives better accuracy when x is small. In particular, if x is 0 or 1, we can get meaningful estimates out the other side, and we cannot do that with the classical statistics. The other big advantage is that it offers the possibility of using prior information to improve the current estimates. In most cases, there won't be good prior information available, and in that case, the Bayes estimation will be very similar to classical statistics. But when there is good prior information available, the Bayes analysis gives better estimates. So if you don't have any prior information available, the option is to use a uniform prior, which gives no external prejudice to the estimation, and it just lets the data speak for itself. The uniform prior is easy to use and it's easy to justify, but it does not confer the advantage of incorporating reliable prior information, and we don't have any, so in that case it's the natural choice. Another possibility is to use a user-defined prior where we do have prior distribution available that is reliable. The advantage, again, is that there's potential for improved estimates, but a big disadvantage is that it may be difficult to construct it properly, and it may be difficult to justify modeling choices. This is an advanced option that's available to advanced users. And a third possibility is to use an informed prior. And this can be used if there are search results from prior years at the same site. The advantage is that you've got the improved estimates, and we've already done the work of creating an informed prior and programming it into evidence of absence software for easy use. A disadvantage is that it's limited in scope. We can only use data from one particular site in previous years for estimating this year's take only. And one final parameter that we enter is the level of credibility required to conclude that a threshold is not exceeded. So this is like a confidence bound in classical statistics. We want to be 80% sure that we're not exceeding the threshold in this case. So we enter all the parameters and we plug it in and ask EOA to get to work for us. And it begins with calculating the detection probability with this very messy looking formula that Manuela showed a little bit earlier. It takes account of the arrival, the persistence, the detection probability, the decrease in detection probability factor to make sure that we don't double count carcasses, and it sums over all the potential landing times for carcasses and all the potential search times. So once we have that, we combine that into a Stump the Statistician game, all pre-programmed into a binomial, just like Manuela was showing earlier. And then it takes another step of combining the overall detection probability with the Stump the Statistician game with a prior information and constructs a posterior. And then when it's all done, it gives us a nice graph that tells us everything we need to know. In the upper right corner, we see that the estimated overall detection probability is 0.167, or about 1 in 6. This is a little greater than the rough estimate of 0.13 that we got earlier by multiplying the coverage times persistence times searcher efficiency. The difference is that the EOA model properly accounts for the possibility that if you miss a carcass in one search, you could find it later on. That rough estimate that we made earlier does not account for that possibility, so it tends to have lower detection probability estimates than the more accurate EOA model. Below that, we see that the probability that the number of fatalities is less than or equal to 8 is greater than 80%. In other words, we can be 80% sure that there were no more than 8 fatalities. Overall, what the graph shows us on the x-axis is the total number of fatalities that may have occurred, and on the y-axis, the probability that the number of fatalities in actuality exceeded the number on the x-axis. For example, at m equals 0, the probability that the actual number of fatalities exceeded 0 given
our observed data, or seeing 0 carcasses in this case, probability that the number of fatalities exceeded 0 or more, is 100%. On the far right-hand side of the graph, we see that it's almost impossible, or a 0% probability, that there were greater than 35 fatalities. It's very unlikely that there were more than 20 fatalities, about 2%. And in the edge of the red region, we see that there's less than 20% chance that there are greater than or equal to 9 fatalities, or we can assert with 80% credibility that the actual number of fatalities is somewhere in the red region, between 0 and 8. In other words, the red region gives us an interval estimate of the number of fatalities. Given the strength of the search protocol and the fact that we found 0 carcasses, we can rule out the black bars with 80% credibility. It may be natural to also ask what the single best point estimate of the number of fatalities is. But there are a number of difficulties with this question when 0 or few carcasses are observed. A naive rule of thumb point estimate that works well when there are a lot of carcasses observed is just to divide the number of observed carcasses by the detection probability, or x over g hat. But when x equals 0 and no carcasses are found, this estimate makes no distinction between the case where detection probability is 95%, and we could be fairly certain that there were no fatalities, and the case where detection probability is 5%, where we can't rule out that there were 20 or 30 or even 40 fatalities, and we just happen to miss all of them. An estimator that makes no distinction between those very different cases has some difficulties. There are additional problems as well. When g is small, x over g hat is biased, and when x is small, x over g hat is unreliable because the uncertainty is very high compared to the mean.
So, for example, if we want to demonstrate with 80% credibility that take was no more than tau equals 5, when no carcasses are observed, we can use the software to come up with a search plan that will get us the desired level of credibility. And we can take into account the searcher efficiency, the search coverage, and the search interval, and what combination of those will give us the required detection probability to demonstrate with 80% credibility. And the solution is to use the design trade-offs module to explore the possibilities. So within the software, we enter the threshold, or the number of fatalities that we want to demonstrate we have not exceeded, along with the credibility level, and in this case it's 0.8, or we want to be 80% sure that we have not killed more than 8. Assuming that we have found 0 carcasses overall. We enter the persistence distribution and the k, just as we did before in the prior and the arrival function. And then we can trade off, look at the trade-offs between search efficiency, coverage, and search interval to find out what combination of these parameters will give us the best optimal way of attaining the credibility level that we require. So in this particular example, we're going to go with searcher efficiency of 0.5, and then we're going to compare coverages from 25% up to 100%, and compare search intervals from 1 to 14 days to see which one give us the best results. We'll ask evidence of absence to draw the graph, and what we see is, in color, the probability that the detection, or the probability that the number of fatalities exceeded the threshold, given that we've counted 0 carcasses. So let's start with the blue. The blue tells us that it is very unlikely that we have exceeded the threshold if we are with a search coverage of 90 to 100% and we're searching on an interval of 1 or 2 days. Under those conditions, we would be very unlikely to see 0 carcasses, and so that's a strong sign that the mortality does not exceed 5. On the other hand, if we only searched 30% of the carcasses and our search interval were 10 days, we'd be way up here in the yellow region, which would say we have very little evidence that the fatality did not exceed 5. So what we're trying to do is find the set of parameters that'll get us as far into this blue region as we can. And what we've said is the real target is to get us to 80% credibility, which is only 20% probability that we are in excess of the threshold. So we're shooting for this line, essentially, this 20% line. And there are a couple of ways we can get to that 20% line. The first is if we have 100% coverage and we're searching once every 9 days. Another possibility is to have 50% coverage and search every day. There are actually a few ways we can get those parameters. One is if we search all turbines out to a long search radius far enough out so that we're sure that we'll get all the carcasses, and we search 100% of the area within each of those, then we can get coverage of 1. If we do that, we only have to search once every 9 days. On the other hand, it's very difficult to search all the turbines, so maybe we can search half the turbines and get a search coverage of 50%. In that case, we'd need to search every day, and those are 2 ways to get the same results. But the top way is preferable. We have searched twice as many turbines, but we're only searching them once every 9 days instead of every day. 22% as much effort, but we get the same result of 80% credibility. Another possibility is that we search all of the turbines and we have a choice. Are we going to search them out to a long radius, far enough so that we have 100% coverage, and in that case, we'd have to search once every 9 days, or we can search every turbine but only go out, search every turbine but only go out to 30 meters, which might cover half the carcasses, so our coverage would be 50%. But if we did that, we'd have to go out every day. In this case, the area, or the ratio of the areas, would be 30 squared over 100 squared, looking at the area within 30 or 100 meters. But we'd have to do 9 times as many searches, because we're searching every day instead of once every 9 days. But in that case, we'd end up with 81% as much effort as the other option. So we can use the software to help design what set of parameters will be the most efficient to get the results that are required. Another trade-off we might consider is searcher efficiency versus the sampling coverage. If we have higher searcher efficiency and greater coverage, well, that puts us more into the blue range. If we have low searcher efficiency and low coverage, that gets us into the yellow range. Not good. To get onto the target, what's the best way to do that? One way this trade-off can work in practice is to compare road and pad searches versus cleared plots. The road and pad searches, you can get great searcher efficiency. For bats, it can be in the neighborhood of 80%, but the roads and pads only cover a small part of the area that usually comprises around 15% or less of the carcasses. You can increase the coverage by searching on cleared plots, but the search conditions tend to be more difficult on cleared plots, and so the searcher efficiency might be only 30%, but the amount of coverage can go up to 80, 90, 100%. Expensive, but it can be done. So if we translate those ideas over to our graph, the road and pad search, we can get the high searcher efficiency, 80, 90%, but we can only get a coverage of 15% roughly, which brings us well short of the target 20% line. So to move up to that line, it's going to be tough to get more searcher efficiency, but if we get higher coverage, we can move up to that line as long as our searcher efficiency doesn't get too low. What we can do, is add some cleared plots, enough to boost the coverage to 50%, and as long as our searcher efficiency doesn't drop below, say, 40%, we'll be at the target of 0.2. A third feature of evidence of absence that will come in very handy is estimation of a multiple year total. So for example, we have several years of search data and we want to estimate not the total in any particular year, but the total that have accumulated throughout a number of years, through years 1, 2, 3, and so on. The software is used to calculate the detection probability for each of the years, and then the series of data is entered into a multiple years page. They'll look something like this. So in the first year, we had a detection probability of 0.3 with some confidence interval and didn't find any carcasses. Didn't find any of the second year, detection probability was slightly lower. And in the third year, we did find a carcass, and at the same time, we changed the search protocol to only do roads and paths and only got 7% detection probability in that year instead of the 25 to 30% we had in the previous years. Combining all this data, we can ask evidence of absence to estimate the total number of fatalities, and again, it will give us the posterior distribution for the total fatalities over the 3 years. In this case, we found one carcass. The detection probability averaged 20% over the 3 years, and we can rule out fatalities exceeding 15, but 15 or fewer, it could well be. As a quick sanity check, let's divide our count, which was 1, we found 1 in the third year, divide that by the detection probability of 0.21, and that is 5 roughly. So if we go up to 5, well, that puts us in about the 50-60% zone. So there's a reasonable chance that we have more or less than 5. That's kind of in the center of the distribution. But if we want to be sure that we have fewer than a certain number, we run up to the roughly 80% credibility level or confidence level in classical statistics. A final use of the evidence of absence software that we're going to discuss today is in the context of a long-term permit. For example, suppose a 30-year permit allows an average take of 2 per year. In other words, we can allow 60 total over 30 years. Ideally, what we could do is track the true number of fatalities, and when that true number of cumulative fatalities exceeds the threshold of 60 that were allowed over 30 years, then we implement some sort of adaptive management action because the fatality has exceeded the threshold and we're not in compliance with the permit anymore. Unfortunately, we never know for sure the true number of fatalities, and we need to estimate. The simplest, most obvious approach would be to use evidence of absence and track the cumulative fatality through time. So we can do that and end up with a graph of the estimated number of fatalities, and we can see that the total estimated fatalities exceeds the permitted threshold of 60 at year 26, which is 1 year after the true fatality exceeded that 26. It could be a year or 2 late, or it could detect it a year or 2 or 3 early. There's a lot of uncertainty about when it will kick in, but ideally, on average, it'll be pretty close. But there's some additional issues. First, the population may well be able to sustain a take of T spread out over 30 years, but the long-term trigger will not preclude that take from happening over the period of just a few years. And if that take is all concentrated in the first few years of a project, say, it may be difficult for the population to recover. Another issue is that the actual take rate, which we're going to call lambda, may not be at all in line with the permitted take rate, which we'll call tau, and we may get a signal of that very early in the project and have warning that we can do something to get the project on track. So if take rate does look like it's higher than the permitted rate, we can implement some sort of adaptive management to reduce that rate to avoid the final take rate exceeding what's allowed from the permit in the end. Or in other cases, we might adjust the permitted take level to match what's really going on in the field. So if we could design a secondary trigger that will fire to give warning that our take rate is higher than is sustainable under the permit, that could be very helpful in bringing down the take rate to acceptable levels and with maintaining compliance with the permit. So the goal is to define a short-term trigger to signal when the actual take rate is out of line with expectations, tau. So to do this, the first thing to note is that an annual take of 2 is much more strict than permitting a total of 60 over 30 years. For example, this is a graph of the exact same data that I showed you earlier with the cumulative take approaching 60 over the course of the permit. But instead of looking at cumulative take, it's the year-by-year take. This data was all generated from a process that has a mean of 2 per year, but about half the time you're getting take that exceeds 2, half the time you're getting take that is less than 2. So if the idea is that your take can never exceed 2, well, the first year of the project you've exceeded 2, and you're in violation of the permit if you define the take in that way, or the permit in that way. So the point is that allowing a total take of 60 in 30 years is much less strict than requiring take to be less than or equal to 2 each and every year. So we'll step back and think about this for a moment. If the primary concern is the effect and viability of a population, or whether actual take is in line with expectations, a short-term trigger to test whether the average take rate is compatible with the data that we're seeing, we can define a short-term trigger to test whether the probability that the actual rate exceeds the threshold is too high. So more intuitively, we can look at this annual take over the course of the 30 years and see if this pattern of take is compatible with an average take rate of 2 per year. So if you think about it for a second, if the average take were 1 per year, it would be pretty strange to see a pattern like this, because almost every year it exceeds 1. Some years it's below, but typically it's well above 1. So an average take rate of 1, highly unlikely with data like that. On the other hand, an average take rate of 4, also highly unlikely. It's usually we're well below 4. Sometimes we're above 4, but it's almost implausible to have a take rate of 4 if that's our data. So what we can do is draw a 99% confidence interval around the average take rate, and it's going to be somewhere between 1.33 and 3. Of course, for a short-term trigger, we don't want to go the whole length of the project before we run our test. We want to check it over the short term. So those first 3 years, what is a plausible range of actual take average rate over these first 3 years? Well, the most likely is a take rate of around 3 on average, But if it's 4, is this plausible pattern to see? Yeah, it doesn't look bad. Or if the rate were 8, it would be surprising to see that many counts so much smaller than 8. Or if it were 1, it would be surprising to see that many counts so much greater than 1. So what range of plausibility is there on the average take rate over that period of time? We can calculate a 99% credibility interval using evidence of absence, and we come up with a range somewhere between 1.61 and 6.78 is the plausible range for taking that particular 3-year span. The most extreme 3-year span in this 30-year period is right in this case, where they're all above 2, and the total is 4 plus 5, 9, 11, 12, 12 in a 3-year span. And it turns out that creating a 99% credible interval for the take rate in that period, we come up with 2.06 to 7.68, which excludes 2. So the permitted take level is outside the plausible range of what the take actually is. In that case, the short-term trigger fires. So with our short-term trigger, we're going to look at 3-year moving averages and test whether the data from the 3 years is compatible or not with a permitted take of 2 per year. So we check in that 3-year period, and we do that throughout the whole period of the permit. And at one point, the data were not very compatible with an average rate of 2 per year. Okay, so the short-term trigger has indicated that the actual take does not line up with the expected take or the threshold. And so there are a couple of scenarios where that could happen. One is that the average take rate is clearly higher than anticipated. In that case, there are a couple of options. One is to implement some sort of minimization and monitoring. It could be, in the case of bats, curtailment at lower wind speeds, increased monitoring to make sure that our rate really is in line with expectations. Or another option would be to reset the take limit based on the projected take, but require some sort of mitigation offset. Another scenario would be that the observed take rate is significantly lower than anticipated at the start of the project. For example, with bats in the Midwest, there's new discussion about permitting with a prophylactic curtailment required at 5 meters per second wind speed at the start of projects. But if the average take rate is clearly lower than anticipated, one option might be to loosen that 5 meter per second requirement and allow either free operation or curtailment at not quite as extreme levels. However, to demonstrate that average take rate is lower than a threshold is more difficult than demonstrating actual take in a given year is lower than threshold. So this turns out to be a multiple year proposition, but over the course of several years, it could turn out to be an important aspect of fatality and wildlife management.
Thank you, Dan. So in summary, I want to emphasize that it's the combination of what was actually killed and our probability of detection that results in what we observe. If actual fatality is very small, we're quite likely to find none. But if actual fatality is large and our detection probability is low, then we are also quite likely to find none. So when we're seeking evidence of compliance with an incidental take permit, it's quite important for us to distinguish these two cases. And the current Horvitz-Thompson-based estimators that we have available to us, and there's several, can't provide the answers that we need. The optimal monitoring protocol may be very different. If your objective is to estimate fatality of general groups of species, like bats or passerines, than when your objective is to provide evidence of compliance with an ITP for a rare species. The target probability of detection is determined by the incidental take permit itself, by the limit that's set, and it won't differ by the species. What will differ is the cost of achieving it, as generally, large species are easier to detect than small ones. But the evidence of absence software provides tools for optimizing design under site-specific conditions. The protocol can be quite flexible and can trade off search area, search interval, and sampling fraction. The new evidence of absence modules that Dan's talked about earlier take advantage of continuous low-level monitoring over the life of the project to identify on a short-term basis when compliance is not met, and a long-term basis when the total take exceeds the overall permitted take. This approach, based on Bayes' theorem, can be used to provide feedback to pre-construction risk models. It can inform post-construction monitoring design and can be used to inform management decisions. The calculations are not simple, but we've packaged them into a user-friendly, peer-reviewed package called Evidence of Absence, the software which is publicly available at this website. It's available for download, it has a user's guide with it, and as always, we are very, very pleased to hear feedback from our users. So with that, I want to again acknowledge the financial support of the Fish and Wildlife Service and the USGS, as well as our co-authors, David Dale, Lisa Madsen, and Jessica Tapley, for their contributions. And of course, thank you for your interest.